First of all, everyone, welcome to our Sensory Hacking 101 talk that we're giving surrounding this contest that Neosensory is running right now in partnership with Edge Impulse over on hackster.io. So if you found out about this talk not through Hackster, definitely encourage you heading over there to check it out and sign up for the contest. We're hoping that this talk will spark some creativity and some inspiration for joining in. So the goal of today's talk was to, first of all, give kind of a little bit of a background and overview about sensory augmentation, sensory substitution, addition, the history of it, the neuroscience behind it, neuroplasticity, the driving force that enables it. And we're extremely lucky that David, my co-founder and our CEO here, was happy to join in and help fill that role. And then after that, we're going to get a bit more into the technical weeds about how you can think about designing these applications in a way that kind of sets you up for as much success as possible. And so, yeah, and we're not going to get too deep in the technical details, but the goal here is to give people kind of a starting point from which you can kind of do your own future research or hop on our developer Slack and ask some more detailed questions. And we'll also leave some time for Q&A, by the way, as well. So with that being said, David, yeah, would you like to take it?
Great, thank you, Scott. And then I'm just going to say a few words just for a few minutes and then pass it over to Scott. I just want to say, first of all, thank you for being here. And it's a real pleasure to have everybody involved. You know, the interest at the heart of our company is about brain plasticity. And I'll just give a word of intro about that, which is that, you know, when you fly over a forest and you look down at the forest, it looks the same way that it has for the last 100,000 years. But when you fly into your destination city, it looks like the whole thing has risen up out of the ground like a motherboard. And it's because of one species. And the whole trick here is brain plasticity or flexibility. For those of you who don't know, brain plasticity is the term that we use in the field to describe the way the brain can change and hold on to that shape. And so the reason it's called plasticity is because 100 years ago, when it was first starting to be understood, the idea was that people were impressed with plastic manufacturing, where you could push plastic into a particular shape and then it'll hold on to that shape for a long time. And that's what happens with the brain when you, for example, learn the name of your third grade teacher. That somehow gets burned into the structure of your brain and held there such that now, much later in life, you can recall it again. I personally have found the word plasticity to be a little limited because, of course, the brain is doing much more than simply changing shape and holding on to it. What you have under the hood there is 86 billion neurons. Neurons are the specialized subtype of cell in the brain that carries information fast. And each one of these has about 10,000 connections with its neighbors. So you have about 0.2 quadrillion connections in the brain. And every moment of your life, this is changing. The neurons are changing their connection strength with other neurons. They're unplugging, they're seeking, they're replugging, they're finding new places. It's like a whole community that is of such complexity that it boggles it bankrupts our language. I mean, we don't have any way to talk about a system of this sort of complexity. But the key thing I want to emphasize here in this case is just the issue about brain plasticity, the fact that we're so flexible with our brains. And I'll tell you how this matters here. I've been studying brain plasticity for a long time, but the main aspect that we're going to concentrate on here is how we take in sensory information. And the key thing to appreciate here is that the brain is locked in silence and darkness inside of your skull. It's not hearing or seeing any of this directly. Instead, all that the brain experiences are trillions of spikes, these little electrical signals zipping around in the brain all the time. And if you represented each one of these little spikes by a photon, the net effect would be blinding, the amount of stuff that's going on in there. But here's the interesting thing. If, you know, when you see, your eyes are registering photons and then turning those into spikes, which go to the back of your brain. When you hear, there's a vibration on your eardrums, which is going all the way to your inner ear, and then it gets turned into spikes. When you touch something, it gets turned into spikes, and so on. So when you look in the brain, if I were to show you with some magical microscope a little chunk of the brain, and you see all these spikes running around, and I said, okay, tell me, is this visual cortex or auditory or somatosensory or olfactory? You wouldn't be able to tell me, because every part of the brain looks the same, because every part of the cortex looks the same, because it is the same. It's all doing the same thing. It just gets defined by what information gets plugged into it. So all of this led me to chew on this issue a long time ago about, could you actually feed in a different sense? Could you make a new kind of sense? And when you look across the animal kingdom, you find all kinds of peripheral devices that animals have that are different. They're picking up on different energy sources, whether that's infrared or ultraviolet light, or ultrasonic or infrasonic sound, magnetoreception, electroreception. You find all kinds of peripheral devices that animals have. But my assertion is that Mother Nature doesn't have to reinvent the principles of brain operation in order to build those. Instead, she gets to just tinker around with the genetics to build these new plug-and-play devices. And so this got us interested in building new ways to get information into the brain. So many years ago, Scott came into my lab as a graduate student, and we set to work on this, probably over 10 years ago now, Scott. And so our goal was to see if we could create new senses. So the thing that we set out to do mostly was sensory substitution for deafness, people whose ears weren't functioning well anymore. And there are about 220 genetic reasons, by the way, where you can lose your hearing. And so many of you know this, we built a vest with vibratory motors all over it, and we captured sound and turned the sound into patterns of vibration on the torso. And people who were deaf could come to understand what was happening in the auditory world around them. 5 years ago, we spun this off into a company, Neosensory, and we also turned the vest into a wristband, Buzz. This is something I think everybody here knows. And with that, we've been able to get this on wrists all over the world. And of course, one of our main interests, that's always been one of our main interests, is what can we do that's not just sensory substitution, which is to say taking, ears and just substituting the skin for the ears, but instead, what can we do in terms of sensory expansion? So for example, you can see a certain set of wavelengths. What if you could see infrared or ultraviolet? What if you could hear the infrasonic or the ultrasonic, things like that? And beyond that, sensory addition. So pulling in completely new kinds of senses, having a sense of the stock market or the International Space Station, or of the CO2 or air pollution in a room, or of electrical fields or magnetic fields, things like this. So this is why we are so glad that you guys are here, because we are pursuing a number of projects to see what it is like to build new senses for humans. And I'll just mention one more thing, which is when we talk to participants who have been, people who are deaf, born deaf, and we talk to them and they've been wearing the wristband for some number of months, and we ask them, what is it like when you, for example, when a dog barks, do you feel a vibration on your wrist and you think, okay, what is that? And you do a cognitive translation that must be a dog bark. And they say, no, I'm just hearing the dog bark. And this is exactly what happened with your ears when you were an infant. You didn't know how to interpret all these spikes coming in your ears, but your brain makes correlations. It looks at your mother's mouth doing this. It has the correlations of the spikes coming in your ears. And eventually it learns how to put these together, and you have just a direct perceptual understanding of your mother speaking. You don't feel like, oh, let's see, there's some high frequencies and some low and some medium frequencies. Instead, you just hear her mellifluous voice. And so this is the thing that we are working on now, is can we build new senses, as in a new qualia, a new private subjective experience that people have with any kind of data stream. And so I'm gonna let Scott take it from here and talk about some of the details of this. And I'm so glad you guys are here to work on these different sorts of data streams. Okay, so Scott, I'm gonna make you host so you can have the video now.
Sure. Awesome. Thanks, David. That was great. Awesome. It looks like you also get to keep your video on too for some reason. Maybe that's the hack. Okay, so maybe before we just take off from here, we can just maybe take a few questions real quick if people have them. I see some on the chat. One person asked, Harrison Tanis, how long does that process take out of curiosity? I'm sure you have a good answer for that.
Yeah, great. It totally depends on the kind of information. So for example, we took blind participants and fed in spatial information about where people were in relation to them. And that was instant. There was zero learning curve there because something about understanding space is very fundamental. In contrast, if you're learning a more complicated thing like the drone and the pitch, yaw, roll, orientation and heading of the drone, and you're feeling that takes a little longer because you have to watch the drone very carefully. And what you're doing is you're seeing, okay, look, I'm making this change, I'm seeing the change and I'm feeling it, and you're establishing that feedback loop. But one of the things that's so important that we're going to talk about today that is really important for everyone to get is that there has to be some sort of feedback. There has to be some correlation with what you can detect. So I'll just give an example at the far end of this, which is one of the things we got interested in was, can we come to understand the stock market, have a direct perceptual experience of the stock market? And for that, what you need to do is have some relationship between the input you're getting and what's actually happening in the stock market. So the way to do that is to make a game where you have a fake stock market and you can move sliders around to feel what's going on so that your brain learns, okay, here's my output, and here's the input. It's got to establish that loop. After you've gotten good at that, then you can listen to the stock market. But you have to learn what it means. Otherwise, it's just random patterns on your skin. So this is the key, is the brain is fundamentally multisensory and it's always trying to link things together. And so that's what you have to figure out with whatever you're doing, is how do you make sure that people learn it?
Awesome. Harrison, also the question, can the process go awry? The equivalent of speaking multiple languages and sometimes mixing them up.
No, in the same way that your vision and your hearing don't go awry. In other words, you never see something and think you heard it, or vice versa. It's the same thing here, where you're feeling data coming in through your skin, whatever that data stream is, and it wouldn't go awry in terms of mixing it up and thinking that you just saw or smelled or tasted something.
Awesome. Cool. All
Great.
right. Thanks, David. Appreciate it.
Yeah, you bet. Thank you guys very much.
Sure thing. And I should have also mentioned, we're also joined by neosensory scientist Michael Parada, who's also been helping us out a lot with both algorithms and our experiments over the years as well. So Mike, David, please feel free to dive in as well with anything you might want to add as we're going through this talk.
Oh, and sorry, just real quick. I saw Harrison on the chat asked synesthesia. Synesthesia is different because a synesthete doesn't actually mix up that he has just seen something. He also has maybe a different quality with that thing, or maybe even will hear something with that thing, but he doesn't have any mistake that he heard something. So it's not a confusion of the senses.
Thanks a ton, David. That was fantastic. Fantastic intro. We're also, just as a heads up, we'll have a link at the end, but we're working on a page that will have a bunch of references for you to dig into, and kind of the history of neuroplasticity, sensory substitution, and some really cool studies there. Okay, so I'm going to sort of pick up and take off from where David left off. And so the goal here and the whole purpose of this talk is to go over how we can design effective, and I'm just going to use augmentation as kind of an all-encompassing term, effective sensory augmentation applications. And so where does one start when faced with the unknown, but start modeling? So what we have is there's some sort of information out there in the world that we care about. It could be from within our immediate environment, such as sound, infrared light, or it could be from somewhere happening far, far away out in the ether, like stock market data or something like that. And our goal at the end of the day is we want to get this information, the information we care about, to the brain. And we do that, the kind of the gateway to that are our peripheral sensory receptors. So as David mentioned, so for example, you have these hair cells in your inner ear that convert these sound pressure waves, they bend and they fire action potentials that convey this information to the brain. You have all sorts of different types of sensory receptors in their body. They're designed for picking up all sorts of information from our natural environment, and they all have their own kind of unique kind of physiological constraints, let's say. So we somehow have this information, we want to get through our receptors to the brain, so we need something to kind of bridge the gap that we know can accurately capture this information and translate it in a way that the receptors that we're targeting will pick up on it as much as possible. So we're going to use Neosensory Buzz as kind of a working example for this. And you can see these links here as well if you want to kind of dig into more of the details. But at a high level, Neosensory Buzz has 4 vibrational actuators embedded in it. These happen to be called linear resonant actuators, or LRAs. And what LRAs do is they vibrate at a fixed frequency, and they let you control the amplitude of the vibration. And these LRAs are in a way specifically designed for targeting a specific type of sensory receptor in our skin called the Pacinian corpuscle. It's a type of mechanoreceptor that picks up on vibration, which is what LRAs do. It turns out you actually have all sorts of other types of touch receptors, some of them what are called mechanoreceptors, like your Pacinian, and these pick up on mechanical stimuli, like stretch, pressure, and whatnot. And you also have other types of touch receptors that pick up on kind of things like temperature and pain. And so all of this is fair game to encode to, as long as you have the right type of device that's able to stimulate that type of receptor. So Pacinians fire action potentials that go to the brain, and the rate at which they fire these action potentials is proportion to the frequency of the vibration, and that happens to be in the order of like 50 to 300 hertz, or the amplitude of vibration. So as you increase the vibration over this range, or increase the amplitude over this range of, say, 0 to 0.1 centimeters, you can actually see the receptor firing rate go up. And I'm also linking to a paper here. Don't worry, we'll have links to all of these at the end. And also these receptors, for what it's worth, can detect changes in vibration on roughly the order of 5 to 10 milliseconds. And this is kind of what Buzz has been designed around. So Buzz has these LRAs, and our LRAs happen to vibrate at a fixed frequency of 175 hertz, give or take, which is well within what Pacinians pick up. And then the Buzz also is able to encode at each of these LRAs the amplitude, which is what you get to control, over 256 or 8 bits of discrete levels, and it's basically around the range also that Pacinians pick up. So if you encode 0, that means the LRA is off. If you encode 255, that means the LRA is kind of vibrating as strongly as the system allows it. And you can perceive this whole range. And so the Buzz LRAs themselves happen to actually be the bottleneck here in terms of how fast you can convey information, but they can change intensity at approximately, let's say, 16 milliseconds. If you try to encode information more quickly than that, if you try to change the amplitude, they basically can't respond fast enough, and that information you're trying to pass through will be thrown out or averaged out. And so this is the frame rate, or the frame duration, the frame period at which Buzz operates. So we have a developer API and SDKs that enable you to plug in whatever information you want to the Buzz, and you can control the LRAs at like 16 millisecond intervals. So at the end of the day, what you have is this device, which lets you take 4 kind of information, 4 signals in parallel, and you can encode them to the skin, get that information to the brain using in 16 millisecond frames, 60 millisecond updates of that information, and you have 256 levels at each site of, to play with. In kind of more geeky signal processing terms, you could say Buzz encodes an 8-bit quantized 4D signal with a 62.5 Hertz sample rate. So if anyone out there has more of a DSP background, that should kind of help you get started thinking about this. Also, shout outs to Rich B and his Signals and Systems textbook. It's free online. Check it out if you want to get into this stuff. So from here on, so like now we have kind of our device, let's say designed, we have it. In this case, we're using the Buzz as an example. And now we want to take some signal and we want to get it to the brain using Buzz or your own device. And so again, we just want to kind of like start by modeling it out is the best way to go. And again, we're not going to get like too technical here. And the goal with all of this is to give everyone a starting point for thinking about the problems that they want to attack. So generally, you can kind of break down the system like this. There's other ways you can do it, but let's just say we have our source data stream that the Buzz is picking up. Somehow, the processing, whether you do that processing on Buzz, which we do, or you're doing it through a peripheral device like an Arduino or a mobile phone connected over Bluetooth Low Energy, you need to take your signal and you want to like get out of it only the key information that you care about. You might not care about all of the data in that signal. Next, you want to make sure that the output of that information, which you've extracted, kind of lines up with your haptic interface and how that gets coded. And so we'll go into all of this in a little bit more detail. And the last piece is, how do you represent that information using these actuators? And what's the most effective way to do that? Lots of ways to do it. Okay, so let's start talking about your source data stream for a minute. So lots of different types of data out there. So I just want to kind of break this down real quick. So broadly speaking, there's kind of two classes of data. There's numerical data, there's categorical data. An example of numerical data would be something like a sound wave. So, and this happens to be a one-dimensional signal in this case. So that means that at any given point in time, you are taking one measurement, and that measurement is the sound pressure level in the environment that your microphone is picking up. You can also have what would be called higher dimensional signals, an n-dimensional signal that's numerical. And so this could be like something like having a bunch of seismic sensors set up in an area, and your goal might be to kind of feed all the information in parallel to, I don't know, predict like an earthquake or something. I'm just making stuff up here. You also have categorical data, of which there's two types. There's what's called nominal categorical data. And so these are categories that don't necessarily have a numerical relationship with one another. So an example might be like types of like states of weather. So like whether it's sunny out, whether it's raining, cloudy, windy, stuff like that. And then you have also what's called ordinal categorical data. So these are categories of data where there might be something more like a numerical representation around them. So for example, you could have a spectrum of how happy to how sad you are. And so maybe you just have three categories that you're taking in, which is how happy, like, are you neutral? Are you happy? Are you sad? So, okay. And so when thinking about the information sources you want to pull, these are general guidelines, and David, Mike, feel free to dive in here. But first of all, the less latency of the information source, the better, generally. And what I mean by that is, let's say I don't know, again, I'm making stuff up, you want to predict the weather. Well, it's probably more useful to get kind of the most recent measurement with as little delay as possible than some weather measurement from like 3 weeks ago if you're trying to predict what the weather is going to be in like the next minute. Also, you kind of want information that changes at periods of less than a few hundred milliseconds. So if you have information that updates, say, every 5 minutes, that can be a bit difficult to train on. So for example, like, free stock market data out there updates like every 5 minutes or so. You can imagine like getting a little vibration every 5 minutes could be kind of difficult to train on. The last, and this is probably the most important one, if you can get it or achieve it, is getting that sensory motor feedback, as David mentioned, is really critical. to be able to train up a new sense passively at least. So the idea here is if your application is one where when you produce some sort of motor output, say for example, like the algorithm that comes out of the box on Buzz, which takes sound from the environment and maps it to patterns of vibration, that means that when I am speaking and I'm wearing Buzz, I can immediately feel the sound of my voice as the vocal cords in my mouth are moving. And that is really useful for being able to train up new senses. If you don't have that, then you need to look at kind of more explicit training paradigms. So you might need to have kind of like a training app where you provide people training data to get used to interacting with that data stream. So again, these are just tips. The more strictly you adhere to these, kind of the better set up for success you'll be. Cool. All right, so let's start digging in. And so before we get started, I promise we'll have some more concrete examples. I'd say the first thing to think about though is now that you've sort of picked your source data stream or kind of you have a rough idea of what you want to do, the more precisely you can define your goals, generally the better, but not required. So for example, if you just say something like, I want to help blind people see versus I want to help blind people avoid obstacles of X size, Y distance away, the more precise you can be, that will help guide, for example, the sensors that you need to choose, how you capture that information, and how you process that information. But that's not to say you shouldn't blue sky things. So for example, some of you may have seen it, I think it's posted on Hackster on our website. Mike made a really cool demo application for Buzz with infrared sensing. And the idea there was to enable people to quote unquote see outside of the visual spectrum with infrared wavelengths. And there might not have been like a specific task in mind, but it's more like, hey, this is a really cool signal. Let's just slap it on ourselves and see what people can end up doing with this new information stream after training up on it. All right, and then the last thing I'll say is, even though something like Buzz or these types of devices can do these sorts of things, that's not the point of them is to not kind of provide basic notifications. So one way to think about this, like anything that an Apple Watch could do, you can do, but that's kind of not the point. You kind of want to try and avoid that. So that's not what we're going for here. All right, so let's get into, now that we've picked our source information stream, what we do with that data once we have it. And our goal here is we want to try to extract only the information we care about, and we want to kind of compress it into a shape, I guess you could say, or a representation that's suitable for Buzz or your own hardware. So we're going to walk through a bunch of examples, and we're going to talk about kind of some of the challenges you might run into, and I'm going to give you some starting points for how you might overcome those challenges. So example one, and this is like the really easy one, let's just say you want to give someone a sense of direction, compass sense. And this one's great and really easy out of the box. So why? So first of all, it's a one-dimensional numerical signal. Buzz has 4 vibrational actuators, so no problem there. You don't need to do anything special with that. The information you care about can probably be fed in slower or even much slower than 16 milliseconds, right? So like if you're getting an update on your bearing or the direction that you're heading while walking at like a few hundred or even maybe a few seconds, that's probably fine for like navigating somewhere. And the last thing is you probably also don't need like a ton of precision in the direction that you're heading. Who cares if it's 312 versus 300 degrees? Maybe you really only just need to know north, east, southwest, and kind of the combinations in between. And then just as an aside, the other bonus here is that this is a potentially low latency application. So you're getting that as you're moving around, you might be getting that immediate feedback being fed into the Buzz, which is great. So this is an easy example of something where you wouldn't have too much to worry about. Getting a little bit more challenging, and I'm basically pulling these examples out of thin air. Let's say you want to like tap into someone's electrocardiogram and feel like the shape of someone's heartbeat and understand like, is this a healthy heartbeat? Is this an unhealthy heartbeat? Is there something wrong with someone's heartbeat pattern? Well, What makes this nice is, again, this is like a one-dimensional signal, so you don't have dimensionality issues to worry about. It's also, again, you have that same bonus where it's low latency, and maybe if the electrocardiogram sensor's strapped to yourself, you can kind of get some feedback to yourself there. But what makes this potentially tricky is there may be interesting information happening at less than 16 millisecond intervals that's useful to understanding kind of the shape of the heartbeat pattern. And so just going back, just as a reminder, the buzz, the vibrational units, these LRAs on the buzz, can only encode information about as quickly as 16 milliseconds. So how can we overcome that? Well, there's a nice trick from digital signal processing called signal decompositions. So some of you might have heard of a Fourier transform. That's an example of a signal decomposition. So I'm probably going to go into the weeds just a little bit here because this stuff really excites me, and I'll try and keep this fast. And if it's confusing, feel free to hit me up over the Q&A or the chat. Again, I'm trusting David and Mike to let me know if anyone's asking questions because they can't see the chat window right now. But so here's just a quick detour on how a signal decomposition works. So pretend this is, zero, over here is 0 milliseconds on the left, over on the right is 16 milliseconds. And this black signal is like what we care about, what we're trying to feed to ourselves. It's this kind of squiggly square wave thing. Well, we can't just tie the signal directly to an LRA because all the interesting information about its shape is happening too quickly. So it turns out what you can do is you can collect all of the little samples in here. So you can collect the 16 milliseconds worth of data, which might be, I don't know, it could be a few hundred little samples that you've recorded. And what you can do is you can break this down into, in the case of Fourier decomposition, a sum of sinusoidal functions. And so what this means here is this black signal is equal to a sum of these sine waves, these 5 sine waves here. And so where this gets interesting is, let's say you're analyzing this frame and another frame of data comes in. These functions, specifically these sine functions, are constant from frame to frame when you do a signal decomposition. So this sine function right here is the same as the sine function in the next frame. What's changing from frame to frame are these values right here, called your coefficients, which says how much of the sine wave there is in this signal, right? So in this case, A is extremely large, this red value. But what's really cool about this is these coefficients are constants for the entire duration of this frame. So you can basically kind of take a Fourier decomposition of your signals in 16 millisecond chunks. You can ignore the sine term component after you've done it. And you can effectively convert this, however many hundreds of samples this might have been, in this example, I'm completely hand waving here, by the way, to just these 5 values that have the duration for this entire 16 millisecond period. So now what you've effectively done is you now have this one-dimensional signal which is changing very quickly over 16 milliseconds, and you've converted it to, in this case, a 5-dimensional signal. You have 5 values that have a constant value for this entire 16 millisecond increment. Really cool stuff. So definitely look into this, and as you look into this, you'll see you don't actually really need to program any of this stuff from scratch. There's lots of, for example, Fourier transform libraries out there in all sorts of languages that can help you with this stuff. Okay, so moving on. Another challenge you might run into is dealing with high dimensional data. So this is kind of the opposite of the previous example. So let's say you want to build a structural health monitoring application. Like there's a bridge, it has covered in hundreds of sensors, and you want to know, like, is this bridge about to collapse? Are there tons of cars going over it right now? Is it quiet? Is the wind making it twist and turn in weird ways like you may have seen in those YouTube videos? And the challenge here is there's a lot more sensors, like hundreds of them, than like what you can pass through with the 4 vibrational units that you have on Buzz or your own device. And so again, so now what you can do to overcome this is apply dimensionality reduction techniques. I'm just listing this here. I'm listing a bunch of them here as kind of launching points for you to look up if this is the kind of challenge you run into. So for example, you have principal component analysis, PCA, singular value decomposition, SVD, k-means clustering you might be able to apply. And then there's also some ways of doing this with neural networks, like using autoencoders. And so with these techniques, you can take a high dimensional data stream and squish it down into fewer dimensions. All right, the next thing is, let's say you want to convert a continuous numerical data stream to a categorical output. And this is more than anything a plug for our partner in the competition, Edge Impulse. But let's say you have a beehive and you want to understand, let's say you hook up like a video camera and a microphone to your hive, and you don't really care about like the all this like raw information coming through. It's a lot of information. The sound the bees are making, you know, how they're moving. It's just too much. It's overwhelming. You just want to know, you know, are my bees happy? Are they angry? Are they getting attacked by like COVID murder hornets? That sort of thing. And so what you want to do, what you can do in this case is where you can use machine learning to build what are called classifiers. So what you can do is you can record a bunch of this data. So if you know, like if you can look at you know your bees and see, you can tell when they're happy or sad. You can record the video, you can record the audio, you can label that as, okay, this is a video and an audio clip where they're happy. Here's a video and audio clip of when they're sad. I don't know. Here's a video and audio clip of when they're getting attacked by murder hornets, right? So you can collect all of this data and you can build up what's called a machine learning classifier. Again, you're going to have, I'm just going to set you off on this path to do this research on your own, but Edge Impulse is a great platform that's free to use that you can look up, where you can go into this easy to use system. You can give it your data and it will spit out, it will just split out a machine learning classifier algorithm for you. And it will do it in a way that can be readily deployed on an Arduino or mobile phone. So check that out. Okay. So that was kind of a tour of all the different ways you can kind of deal with beating these kind of different data streams into shape, to molding them into shape. So now at the end, so now you've done that. So what you're left with is, in the case of having a numerical signal, you need to now kind of map it to a range. This is kind of, it's pretty minor but important. You need to map it to a range that's suitable for encoding to the LRAs on Buzz in this case. So as I mentioned, the LRAs take values between 0 and 255. Whatever you've done, you might end up with like a signal or a collection of signals that could have numerical ranges anywhere from like -500 to 300, 0 to 5,000. It could be all over the place. The important thing here though is you want to capture as much of the LRA dynamic range as possible. So what you might do, so what you should do is, like, let's say your numerical output is on like 0 to 1,000. What you want to do is you want to scale that output down to 0 and 255, and then apply that to the LRAs instead of trying to feed 0 to 1,000 directly to this 0 to 255 level where you're going to like max out at 255. All right, and so the last thing we're going to get into, and I'm sure David and Mike might have some ideas here, things they want to add, is how do you haptically encode this data in a way that's effective? And this really becomes application dependent very quickly, kind of as all of this has, but hopefully will give you kind of a good way of thinking about things. So with Buzz, and for example, you have 3 dimensions to play with. So not only do you have the intensity, the amplitude of the LRAs that you can play with, but you also have space and time. So for example, you have 4 LRAs. So you can create interesting patterns across these 4 LRAs. And with time, if you don't care about feeding information through at the 16 millisecond kind of limitation, if you can apply your information a little bit more slowly, you can do some really interesting things. So for example, and actually I'll start with this. So here are some ways you can leverage space and time. So you can create spatio-temporal patterns, or you can create textures, and these can be well suited for categorical data. So with spatio-temporal sweeps, the idea here is you can turn actuators on and off in quick succession. to give the perception of patterns moving across your wrist. So for example, like if you just want to know like whether it's, if you're just like classifying whether it's sunny or rainy out, you could have a sweep that goes counterclockwise or clockwise on the buzz that represents each of those. If you also have a bit of time to play with, you can also create textures. So you can create interesting little patterns that turn the LRAs on at different intensities. And you can tie these patterns to your categorical output. So you could say, I don't know, like maybe you have an alarm. Alarm's not a great example, but maybe you want to try and get someone to be, I don't know, sleepy versus awake. So maybe there's some patterns you can apply where you have a slowly kind of a very soft texture-y kind of pattern when you're trying to get someone to become tired, or more like intense kind of buzzing texture when you're trying to like get someone to be more awake. The other thing you can apply that I'll also mention, another hack for encoding signals is to use illusions. So here's a pretty well-known illusion. The idea is that you can actually, if you turn two adjacent actuators on in some proportion, you can create phantom vibration sensations between those two actuators. So for example, if you turn on actuator 1 at 50% and actuator 2 at 50%, you'll feel a vibration actually interpolated somewhere in between the two. And you can move that around by adjusting these proportions. So you can turn on one at 75%, the other at 25%, and that will bias where that kind of phantom vibration occurs somewhere in between, more towards the stronger vibration. The other thing you can do is you can kind of add on an overall gain factor to this. So you can even, so you can create these locations of vibration, but also mess around with their perceived strength a little bit as well. And so this is great if you want to output, like, for example, a two-dimensional signal where one of those dimensions has a spatial component. So like going back to like the compass example, like if you want to say you're headed in a specific direction and you want it to vibrate more strongly as you're getting closer to something, right? You can use this illusion to say where, like the where on the wrist is the direction that you're headed, like towards that, like how towards that thing where you should go, and then like how strong, and then you can add this gain factor for like how close you're getting to it. So the other thing I should have mentioned, which is kind of more straightforward, was if you just simply if you're able to squeeze your information stream down to like 4 dimensions that kind of fits all these constraints, you can just directly apply then those 4 signals to those 4 actuators and change those in time. So that's about it. So hopefully you have a pretty good starting point for getting going. The last thing I'll say is, now that you prototyped your app, now what? Well, then you should totally run experiments. Try this on yourself. Definitely encourage people to like journal your daily usage. There's a lot of great research papers out there where people have strapped on weird devices onto themselves and they keep a daily journal. And those are really cool papers to read. I'll be sure to add some of those to the website, which I'll link to in a second. And the other thing you can do is, and probably Mike and David can provide some great input here as well, is like run your device with users and run an actual study, build some training games, have people test this thing out to train on daily, and build test games to assess performance at specific tasks. So yeah, that is about it. Thank you, everyone. Thanks for staying through this webinar. Hopefully this gave you some inspiration and a good starting point for joining in our competition and building your own applications. Join our Slack channel. I think Jenny, who's been an immense help with the competition, just posted a link in our chat a bit ago, and you can also see it on our website. Should have linked to some more stuff here. But this is where we'll be posting the webinar resources on our GitHub.io page, Neosensory, GitHub.io, Sensory Hacking 101 webinar. Right now for the competition that we're running, you have till this Friday to submit your ideas to win a free buzz to work on it. But you can always still buy one if you don't actually win one of the buzzes to participate in the competition. Let's see. Okay, I'm going to take some questions. So actually the easiest, I'm going to look in the chat, but because I haven't been watching this entire time, I might have missed some. So feel free to use, oh, here's the Q&A session. All right, I'm going to answer one I saw in the chat real quick. Is all the processing done using access via SDK? Yes. So with the Buzz right now, we provide access to controlling it through a Bluetooth low energy link. So you can connect to Buzz using any Bluetooth low energy device, whether it's an Arduino or a mobile phone. And our API enables you to control the vibrations however you want on these 16 millisecond frames. We have software development kits, SDKs. So these just make the job of programming applications a little bit easier. They're not required, but we have SDKs for, let's see, Arduinos, specifically at the moment, the Bluefruit Arduinos. You can get all the information about the supported Arduinos by looking at the documentation on our GitHub repo for it. We have an Android SDK, and we have an awesome, someone from our developer community actually was awesome enough to contribute an iOS SDK. So that's kind of what we're supporting out of the box at the moment. But if you're using a different platform, you can refer to our API documentation, and that should technically be enough to get going. Okay, let's look at some of these answers. Thank you for the comprehensive answer. All right, I will mark that as answered. All right. Can you use the new haptic feedback vests that are being released for VR, for example, B haptics, in the same way as Neosensory Vest Buzz? Yeah, you're just going to have to look up what they support in terms of control. Not sure about that one. Another question. How do you submit multiple idea submissions on Hackster? That's a great question. Let's see. I don't know if that might be a great question for Jenny. I'm not able to immediately answer that. I guess please do ping us again, either in our developer Slack or on the competition page itself, and we'll try and get that answered for you.
Jenny seems to have just posted.
Oh, what was that? Oh, great.
Jenny seems to have just posted on.
Oh, awesome. Fantastic. All right, another, let's see. I saw a question about an accelerometer. We do not, there is no accelerometer on Buzz that is accessible. How do we, let's see, is there any feedback from the device? Sorry, any feedback from the device available via the SDK? I totally apologize. I don't actually understand the question. If whoever asked that, Brian, if you're able to clarify that. So those are all the questions I have right now. So again, yeah, we'll keep a few more minutes open. Glad to see we still have 35 attendees, and I didn't bore you all to death and we're down to 2 people or something, or just the group of Neosensory employees. But stick around for a few more minutes if more questions come up. In the meantime,
and Scott, if you click on answered, you'll see that there are a number of questions that Mike and I have typed answers.
Oh, that's awesome. All right, thanks for doing that, guys. That's great. Cool. Awesome, 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 awesome.
All right, any other questions? Any questions at all? Throw them into the Q&A or the chat.
Cool. Mike, David, anything you think I should have added?
We have a blog post on how, what the ideal way to make your application is. So check that out. Essentially, this is just repeating something that Scott emphasized, but you want to make sure that if you think of something that's like an alert, that's not actually what this is good for, because you could just use an Apple Watch for that, or use your phone if it's simply an alert. So what you want to think about is, how can I pass a real-time feed of data that is useful in that way? So if anything strikes you like, oh, I'll just buzz when this happens, throw away that idea and do the next one.
Yeah.
All right. I think oh yeah, go ahead, Mike.
Oh, just yeah, great job. I'll just emphasize that if anybody is intimidated by the signal processing stuff, one, Scott gave a lot of great resources, and you can dive into those and learn those. And 2, there are a lot of applications where they can be very successful that don't need as much advanced signal processing. So don't be intimidated. Dive into stuff, even if you're a little worried about that.
Yeah, absolutely. That's a really, really great point, Mike. And also, yeah, join our developer Slack. You can go to neosensory.com/developers for the link to that. And we have an amazing community who's more than happy to help, who are more than happy to kind of help brainstorm ways you can design your algorithm. So great. All right. Thank you, everyone. Oh, and now there's all these last minute questions popping in. Let's see. Other question. All right, we got the Hext one. Is there any feedback from, okay, we got those. Can the buzz trigger audiation with people that hear? No, not at the moment. You can only encode information using vibration, using the LRAs on the device. There's no speaker on it or something. That gives us audio.
I think maybe I'm guessing his question means if you already hear,
yeah,
and you develop infrasonic or ultrasonic sound, something like that.
Good call. Yeah.
Yeah. And the answer is yes. I mean, it's easy to pull that kind of information and then feed that in. It might not. The difficulty there is just getting the correlation, which is to say, if there's really, really low frequency sounds, really, really high frequency sounds, they often don't have anything to do with what's going on in your hearing range. And so it just ends up feeling like random noise to you. But yeah, you can totally pick up on it, and you can work out ways to make those correlations more clear, like having an audiogram that shows the whole spectrum.
Yep.
And to add on top of that too, in case it's also asking about the normal hearing range, if somebody who is not deaf or hard of hearing wears buzz as it is now around, you will have a blocking phenomenon where your brain already has all the information it needs about that sound via the ear, and so it doesn't dedicate the energy or resources to the space on your wrist, so it doesn't start hearing via the wristband if it's just representing information that your ears are already representing.
Arnav asked, does the solution have to solve a problem? Can one submit something that has educational value, for example, helping kids feel Wi-Fi signals or radio waves? And I think the answer is definitely not, but let me know what you think, David. It's just giving people new senses is a great thing on its own. Cool. Oh yeah.
Yep.
Can a user grow accustomed to the vibration and just learn to ignore it? This is a good question for you, David. How much time do we have to train a human?
Yeah. The general answer is you can ignore it in exactly the same way that you ignore the feeling of your pants on your legs. You don't typically think about it there, but if you concentrate on it, you can be aware of it. So the whole key is that somehow the data coming in has to have some relevance to you. You have to care about it for some reason, whatever that reason is. So one of the general strategies here is to set things up in terms of a game where you've got people playing a game and winning points so that they come to care about the data that's coming in. And so I'm not positive what the root of your question was, but yeah, you could ignore the data if it's not useful. But also, even if it is useful, you don't have to pay attention to it, which is cool. Unlike a computer screen where you have to really look to get data from it, if you have something coming in haptically, you end up just attending when you need to. Exactly like with your shoe on your foot, you're not paying attention to it, but if you get a pebble in it suddenly, then you will pay attention. So I hope that answers the question you were asking.
Great. Yep. Awesome. And then Harrison asks, is there a special reason that Buzz targets the wrist as the haptic input site aside from convenience and ease of adoption?
I can jump in on that. It's just that, other parts of your body have higher receptor density, like your fingertips or lips. But one of the most important things to us was to make something that people would actually wear. And it turns out that people are super happy to wear a wristband that looks like a Fitbit, but no one actually wants to wear a vest around all day. And certainly people don't want to wear a glove or something on their face. So it ended up being the perfect part for us, the perfect part of the body for us to concentrate on that took care of business that way.
Yeah. Great. And I answered in text, but I think someone asked if we'd be posting the slides Yes, we'll post the slides up. We'll probably be on that github.io page that was linked to, and we'll message that out over the discussion page on our Hackster contest site. So great. All right, I think that's everything. Oh, yeah, no, that is everything. All right, thank you, everyone. This was a blast. What a great response and turnout. That was awesome. So just in closing, go ahead, David.
Nope, that was it. I was just saying thank you.
Awesome. And yeah, so just a reminder, sign up for the contest, join our developer Slack. A lot of great people and ideas floating around. All right, take care, everyone. See you around. Bye.